So welcome everyone. So today, Philippe Gimenez from the Universidad de Valladolid is going to tell us about how to construct the short resolution of a weighted homogeneous ideal.
Okay, thank you. So I first want to thank the organizers of the seminar and also of the event here. I'm very glad to be here. And during this talk, I'm going to present some recent results. This is a joint work with Ignacio Garcia Marco from the University of La Laguna. This is the Canary Islands, so if you want to visit. And Mario Gonzalez Sanchez, who is our joint PhD student. He's almost done with his thesis. Okay, so I will start with some notations. We will work over a field that we assume infinite, just to avoid some problems. And so we will be in a ring with n variables, and we consider a weight vector omega and an ideal that we consider weighted homogeneous. Means that we allow us to give weights to the variables if it's needed. Okay, so and this is the weight of x1 and the weight of xn. Okay, so let's assume that D is the dimension of the ring, and my main hypothesis here, and I'm going to convince you of several things, that it's not a very strong restriction, and also that it may help to do new things, is that we are going to assume that the polynomial ring in the last D variables is another normalization of the quotient ring. Okay, so I'm going to remind you a little bit what this means, how we can reach that, and also when this is already given for free before starting to work. Okay, so this essentially means that this is an integral extension. So let's, and when this occurs, this gives to our overall a structure of finitely generated A module, where A is this smaller ring. Okay, so let's recall some facts. Or maybe I could. Some facts on normalization. By the way, when this occurs, we would say that the variables are in another position. I will explain why we call this way. Okay, so several facts on normalization. I will take some time in this talk to insist on all these things, and I will go very fast at the very end to present our results. It's more important for me to convince you that this short resolution that has not been studied a lot is interesting. Okay, so the first fact is that we know that one always has that there exists some elements, D elements, D is the dimension, I recall. here that are independent, which I mean algebraically independent, that is, that the ring K of C1 CD is isomorphic to a polynomial ring in B variables. So there always exists inside this elements such that K of C1 to CD is another normalization. Okay, so this is always possible. But also, we always know if the field is infinite, where it's important, how to find some of those elements. So what we can do is basically a generic change of coordinates in our ring, and then d of the variables will be that way. And if we choose the change of coordinate, it does not need to be general. I mean, a triangular one is enough. And if we choose it correctly, we can always assume that the last d variables or the first d variables, whatever we want, are the variables that fill the condition. Okay, so a generic change of coordinates. In general, it's enough to take it triangular, and even I would say something later, smaller ones provides. I would say puts variables in nutter position. Okay. A third important thing is that we have a test. We can check if this occurs or not. So we have a test for nutter normalization or for nutter position, which is the following. There will be a little of Grosvenor basis in my talk, so I hope that you're all familiar with this. Otherwise, I will try to explain a little bit more. So if we consider, oh, sorry, I wanted to say something here, which is sometimes important. I have assumed my ideal weighted homogeneous. If I need to do a change of coordinate to have this, this can be destroyed by my change of coordinates. So we have to be careful with that. Homogeneous can be destroyed by change of coordinates. But if my idea is truly homogeneous, I have no problem. Then I can do a change of coordinates and it will still be homogeneous. But it's okay if it's standard homogeneous. Okay. So the test for another position, this is for I homogeneous, standard homogeneous, is the following. If we have the dimension, and if we consider the graded reverse lexicographic order, so for people that are used to Grosvenor basis, this is one of the way of ordering our monomial, which is very specific. It's known to be as the most efficient one in general. So if we consider this order n, we denote by n of I the initial ideal, which is the ideal generated by the leading terms of all the polynomials in I, with respect with this ordering, then K of x n minus d plus 1 to x n is another normalization of R over I if and only if, oops, So if I can read that on my initial idea, what has to occur is that the first n minus d variables must appear in a pure power. Is that really the integral dependence of those variables on the other ones? Okay, so for all I from 1 to n minus d, there must exist a power of xi in my initial idea. Okay, and because the dimension is d, this means that the other variables cannot appear as a pure power, otherwise the dimension would be will not be d, and also the rest of the generators must involve all of them those variables. We think about the radical, if this occurs, will be x1 to x minus n minus d. Okay, and all the rest of the generators in the initial idea must be killed by those variables. So some of those variables are there in the other generators, and the other ones appear in some of the other generators or not. Okay, so the fourth thing I want to say, just to convince you that this is not so restrictive, is that there are families of ideals where we already have normalization. For example, the family of toric simplicial ideals. So instead of telling you exactly what this is, because otherwise I will not have, I'm going to show you one. Okay, whoa, surprise. Okay, so a toric ideal, how do I define a toric ideal? I would take a set of elements in n to the d, okay, and we'll consider the semigroup generated by this, and associated to this, I have a toric ideal, which can be defined as follows. If I consider this morphism into a polynomial in d variables, those are the parameters, those are the variables, and I will send xi to the monomial t to the ai. Okay, so this is a way to define parametrically my toric ideal. Okay, so if I do that, the kernel of phi is an ideal which is prime, binomial. This is a toric ideal. Okay, and that's the keyword, simplicial. What's important for me to have another normalization is that if I consider, let's assume that this is non-degenerate. That means that the dimension of R, this is R, of R over IA is D, indeed, the number of parameters. If it's not, then I can change my parameterization and find one where it will live in a smaller space. Okay, so when this occurs, if I want another normalization, what I need is to have that D of those elements, of those n elements, have to generate the rational cone generated by those one. What does this mean? So here is an example. Here D is 3, N is 9, okay? And I consider this morphism where I send for, so I have 9 elements in N3. So how should you see that? This lives in N to the 3, okay? I have the 3, those 3 that are on the coordinates lines, okay? And I have other of those ones. So these are 9 elements in N3. You see that all of them, the sum of them of the entries are 3. Okay, so you have to see that as I have a cone, the rational cone generated by those 3, and the other ones are when I look, I cut this way, are located on those. In fact, there's just one missing here, which is the 1, 1, 1. Okay, that's a kind of punched fairness. Okay.
So the fact that there's one missing means that this is not normal. But what does
Yeah. Let me see if when I say toric, I mean non-normal.
That's fine. That's fine. But you said something about simplicial.
Yeah.
How do we see that? See the simplicialness of parentheses?
Yeah, simplicial means that here in N3, I need 3 vectors that are that generated the cone where everybody lives. Okay, so I cannot have this. I need this. Okay, so
I thought you said something about how to see down correctly, but maybe
no. That I mean, I look on my at my generators, and I need to them to be okay. But yes, I could use what I've written before. Maybe here. Let's see. I can see that here. If I do that, I mean, in order to compute this ideal, you can do that with Grosvenor basis, for example, eliminating variables T1 to TD. And if you compute the initial ideal of this ideal with respect to your Grosvenor basis, then yes, we can use that. Okay, so if in this situation, I already know that the initial ideal of this ideal will have a power of all the first 6 variables and maybe some other generators involving all the variables. All of the generators must involve at least one variable between x1 to x6. That's the criterion I wrote. Okay, so this will occur here exactly. So okay, so why? So yes, so anytime this occurs, anytime I'm in this situation, then the polynomial ring in the in those variables, in the last 3 variables, is another normalization of my quotient ring. Okay, so when this occurs, if it's simplicial, okay, if it's not simplicial, you see, if I have 4 vectors in my cone, then it's not, I do not have 3 variables such that the other ones are integral of them. Okay, so it will not work. So I really need it to be simplicial. But when this occurs, so I can build anytime I have a simplicial semigroup, I can build an example where my conditions are fulfilled. And also my condition on being weighted homogeneous is also always fulfilled for toric ideal. If I give this weight, those could not be on the. I mean, the weight of this of all of them is 3, but I could have some of another weight. That would be okay if it's simplicial. Okay, but this one in particular is homogeneous, standard homogeneous. Okay, but that's because the weights are the same, but this could not occur. Okay. Okay, so why am I interested in this condition? So when I have under my conditions, okay, so I remind this means that A, the polynomial ring in the last D variables is another normalization of RI, and I is graded homogeneous. then Ry can be seen as an R module as usual, or as a module, as a structure of finitely generated R module or A module. So I can think about its minimal graded free resolution as an R module, as I always do, or as an A module, which is what I'm going to call the short resolution. Okay, so it has a minimum graded free resolution as R module, which is the usual one, and also a minimal graded free resolution as A module, which is the one that I will call the short resolution. So we can think that it's short because I have less variables, and that's true, yeah.
I'm a little, so I'm confused by the grading because
Yeah.
are the change of coordinates that makes like
Oh.
or like the change of coordinates might destroy
Yeah.
grading. So when you say graded free resolution as an A module,
Yeah.
what's the
Yeah, I'm assuming, I mean, my hypothesis is I do not do change of coordinates. I'm assuming that I have already variables in natural position. Okay, if I have a weighted homogeneous ideal and I want to put variables in natural position, it's not that easy as I want. If I do it with a change of coordinate, I'm going to destroy homogeneity. Okay, so the thing is that I'm going to assume that this is already the case. For example, it's the case here. It's the case in a lot of situations where I can do that, and sometimes it will not work. I mean, sometimes I will not be able to build this minimal graded free resolution as a module when this one is good. Okay, yeah.
That if you have a finite multigraded algebra, you can't find a multigraded another normalization of it all?
I don't think so. I don't think so. In general, that you will lose your grading, which is an issue for us. So I don't pretend to say that this will work always. I mean, sometimes if we do not have natural normalization and we can get it, when it's truly homogeneous, we can always do that, and the field is infinite. And sometimes I cannot do that. Okay, and sometimes I already know I have it beforehand. That's what I wanted to tell. Okay, so why am I interested in this short resolution? But essentially because it's short. And I'm going to show you in this example. Oh, okay. So I didn't have time to write the whole Betty diagram of the first resolution, the usual resolution, but it has 8, with this one, 9 steps. And here the short resolution has only 2. Okay. So what is interesting is that some of the information that I can read here, I can also read it here. For example, the Hilbert series. The Hilbert series, I can compute it here, but I also can compute it here. And what is the difference? Is that when I compute it here, it will already come simplified. You know that the Hilbert series, you have a factor 1 minus t to the n and a polynomial here. And then you simplify it until you reach this, okay? And with another polynomial here. And if you use this, you will already get that one, that form, okay? So tell us to compute the short resolution allows to compute. So the Hilbert series, for example, But also, for example, the Castelnau moment for regularity that we mentioned on Tuesday, sorry. So the Castelnau moment for regularity, which is the maximum regularity of all the shifts in my resolution minus the step where they occur. For all for all the steps, and I can do that here or here. Yeah. Oh, because yeah, I get the same answer because the Castelnau moment for regularity is also defined with the local cohomology modules, and there's an independence theorem there that says that it does not depend on the ring where you're looking at it. Okay, so it will be the same thing if you do this here and this here. What does this mean? It means that the number of rows, the number of columns is very different, but the number of rows, which is the Castelnau moment for regularity, will be the same. Okay, which is the number of rows in the Betti diagram. And why is it short? Can be very precise, because also there's another thing that I can compute that does not depend, is the depth. The depth of R over I does not depend if I consider R over I as an R module or as a module. And the depth is related to the projective dimension by the Auchlander-Buchbaum formula. Okay, so what we have is that the projective dimension of R over I seen as an R module is the projective dimension of R over I seen as an A module plus n minus d. Because this is by Auchlander-Buchbaum the depth n minus the depth, and this is by Auchlander-Buchbaum d minus the depth. Okay, so this gives this equality. In particular, sorry.
The depth is equal to n1 step. You need n1 step. What is the?
Yeah. Oh. Sorry, that's my Spanish. That is appearing when you don't expect it. Okay, that's the projective dimension, sorry. Okay, so the projective dimension of the big one is the small one plus n minus d. In particular, you see that the Cohen-Macaulay property, which are the ones where this one is the shortest, is also the one where this one is shortest. And this will occur when this is n minus d, so when this is 0. So what does Cohen-Macaulayness means in terms of the short resolution? It means that it will only have one step, or in other words, that R over I seen as a module is free. Okay? So I guess there is something here. Yeah. Okay, so on that note, R over I is Cohen-Macaulay if and only if the projective dimension of R over I as a module is 0, which means that R over I is a free A module. So everything seems that if you can use it, well, it should be better. What's the problem? The problem is that we know how to construct this resolution. We have several methods all of them more or less involving Grosvenor bases, which say, how can I compute a minimal graded Fourier resolution of R over I as R module? I can compute the Grosvenor basis of my generating set of generators of my ideal. If I have a Grosvenor basis, the reductions of the S polynomial. So this will just mean something to people that know about Grosvenor basis. Would give you the syzygies. I mean, you read the syzygies on the reductions of the S polynomial. And once you have the first syzygy module, you do that again, and you compute a new Grosvenor basis of the syzygy module that you have described, and you will get the next syzygies, and so on and so forth. And that's a way to construct this resolution. That's the way it is implemented in Macaulay 2, Singular, and all those packages that do this very, very well. Okay. There's, yeah.
Have a lot of non-standard grading. This board I know how to make sense of in the standard graded
No,
case.
all this is, oh, yeah, sorry. I forgot to say something. Of course, when I talk about regularity, I mean the standard grading. The resolution could be a graded resolution for my omega grading, okay? But for omega grading in general, I could talk about the omega regularity, but this does not make many sense, okay? So this regularity, this is because this is if I is standard homogeneous, okay? I can talk about the omega Hilbert function. This I can do that. Okay, so all this I can do it for omega grading, but when I talk about regularity, yes, it's true. It's homogeneous.
Alexander Buxbaum, I want to be in a local ring, and if I'm standard graded, I can definitely localize with the homogeneous maximal ideal. And
Yeah,
yeah. And otherwise, we're just localizing it some maximal ideal that contains I.
That's it. Yeah. Okay. So, but I mean, I have a omega graded resolution. I mean, if I have my grading, my omega grading, I can define my omega resolution over R or over A, both of them. Okay, I'm going to maybe in a moment say.
What this actually remains when you use any linear system of parameters? Like, is your assumption something about having a special linear system of parameters somehow?
No.
So
What?
if you start from any linear system of parameters, I guess you get normalization, and I assume that some specs stay, but holiness response to having something straight.
Yeah.
Are you assuming something more, like setting something more beyond products?
No, I'm not assuming anything. I'm just assuming that I know beforehand, in general, that I have this not normalization, and that my ideal is omega graded. Okay, but of course, if I do not have those things, then I can lose my grading if it's not standard homogeneous. Okay. No.
Confused about the non-standard case. So over there for this, Cohen-Macaulay can only short resolution. I'm happy for that to be, Cohen-Macaulay at a particular point. But is there some, in the standard graded case, then we're actually
Yeah, because you're translating. I mean, the local thing is, I guess you need your it's related with the graded situation when you have the standard grading. That's it. But you also have graded resolution, non-standard graded resolution. You can use any grading if you forget about the local situation. If you have your ideal, which is omega graded, then you can define your resolution. Yeah, and you can make it graded. and it will have an omega graded, and it will have an omega graded free resolution. And you can read all those things. I mean, you can do, once you have your graded resolution, you can focus on a degree, an omega degree, and have and read your Hilbert function and so on.
I'm very happy for non-standard grading for the Hilbert function. It's for this use of Auslander-Buxbaum that
Yeah.
I've become worried.
Yeah. Yeah. Maybe you're you're right. Maybe.
I think you can use the ideal generated by all the variables in the same way that you can grade it.
As long as the gradings are all positive.
Yeah.
Yeah, it's a positive.
Yeah.
Oh, yeah.
But so there's still an issue where in the standard graded case, then it's true that the ring R mod I is Cohen-Macaulay if and only if R mod I look like the homogeneous maximal ideal. of
Yeah,
Cohen-Macaulay.
yeah.
In the non-standard graded case, I don't believe that is a theorem. And so then I don't know, then I'm happy with Cohen-Macaulay at that point. But
Yeah.
I don't know how to get R mod I.
Yeah. You're right. Let's. I will answer you later, but maybe you're right. If I use the Auslander-Buxbaum, maybe I'm not sure. I'll look.
Sorry.
Okay, okay. So let's, if you want, assume that it's standard graded. Okay. Okay. So what is for did I want? So what do we need to construct this? How can we construct the short resolution? So what do we need? We need, in fact, two things. We need a system of generators as a module, and we need the syzygies, the first syzygies. So we need a system of generators of R over I as a module. And this was known. And we need a system of generators of the first syzygy module. Once we have that, we can do exactly the same as we do here. I mean, we can use Grosvenor bases to compute. This gives the first steps of your resolution. Then you can use your Grosvenor bases of the syzygy module to build the rest of the resolution, and you get it. Okay. So usually for the minimum grade free resolution as R module, this already provides a method to construct the minimum graded for resolution. The resolution. And the same will occur with the A resolution. Okay, which is not the best method to compute it, but it's one method. I mean, I have my generators. Okay, I compute a Grosvenor basis, and that will give the first syzygies. And then I compute the Grosvenor basis of this first syzygy, and this would give the second syzygies, and so on and so forth. This requires a lot of Grosvenor basis computations. So that's why it's not very efficient. But then you also have, so this is a kind of Buchsberger-like method. But you also have the Schreier resolution. which is in general a more efficient way to construct your resolution, which is as follows. When you compute the syzygies through the Grosvenor basis, then you get a system of generators of the first syzygy module. And Schreier proved that for some term ordering that he defined on the first free module in your resolution, the set of generators that you obtain is already a Grosvenor basis for this new order. So you do not need to compute another Grosvenor basis. You have it. So these Grosvenor bases will give you the next syzygy module. And again, this system of generators will be a Grosvenor basis for a new Schreier ordering on the next free module, and so on and so forth. So you just need a Grosvenor basis computation at the beginning, and the rest will follow. But the resolution that you get is in general non-minimal. So you can make it minimal at the very end. And this is in general more efficient than making it minimal at each step and compute a new Grosvenor basis and so on and so forth. Okay, so this is another method. Which is in general more efficient. Okay. So let me tell you what occurs with the short resolution. With the short resolution, we have in fact the same results, or very similar results. Oh, so let me mention the resolution is in general non-minimal, which is important. Okay, you will have to make it minimal, but this will cost less than computing all those Grosvenor bases that you need to compute with the first method. So first, let me give you the known result. Oh, I should say a little of history of this short resolution. It was introduced originally by Pilar Pisson, and then later by Ojeda Vigneron. And this was, in fact, in the toric setting. This was for lattice ideal, and this was for, in general, rings of semigroup rings. Okay, and then it was later by Bermejo, Garcia, Llorente, Garcia Marco, and Morales, also in 19. This was in general. When your hypotheses are fulfilled, okay? And what you have here is a system of generators of RI as a module, which is given as follows. So that's a proposition which says that, again, if you use your Grosvenor basis with respect to the graded reverse lexicographic order, consider this one, the omega graded reverse lexicographic order, then if I consider the set B0 of the monomials in R that do not belong to the initial ideal plus the last n minus d variables, the last d variables, sorry, then I could say that the set of the classes of those monomials of the U is a minimum generating set of Ri as a module. Okay. So, few things. Your initial ideal, remember, if the variables are in a superposition, they have few powers of the first n minus d variables. Okay? So what I'm doing here is I'm looking below the staircase. What are the monomers that are not in my initial ideal? But I'm adding the variables that do not appear. So what this means is that the number of monomers that are not in this ideal are finite. There's a finite number of monomial under my staircase. If I do not do that, I have infinite monomials. Okay, so I add those variables, and what they show in this paper is that the classes of those monomials in Ri are a minimal generating set of Ri as a module. Sorry. Oh yeah, thank you. That's excellent. Thanks. Okay, so this means that the beginning of my resolution will look as follows. In fact, indeed, we can say what is the first step. The first step and how you have to grade your first module. So this is the sum for all the V in my B0 there of minus the degree, my omega degree of those monomials. Okay, so the first free module has to be graded that way. And in fact, this morphism is exactly the one that will send the corresponding, you have your canonical bases here, epsilon 1, epsilon, the number of elements are in B0 that I have here, okay? And I will send the element here to the class of the corresponding monomial. Okay, that's my first map in my resolution. Okay, so I know the gradings, I know how many degrees I have, and in fact, and this is also minimum for the first step. Okay, so what we need now is to describe the kernel of this map. So the way to describe this, as we said before, if Ri is Cohen-Macaulay, we are done. Then this is free, and this ends here. Okay, so if it's not Cohen-Macaulay, one knows that, and that's also because of this reverse lexicographic order. Otherwise, there are monomials in the initial ideal of phi that involve the last. I mean, in my initial ideal, this one, remember, I always have powers of the first n minus d variables. Then I have more generators, and all those generators involve at least one of the variables, the same ones. But some of them, or maybe no, will involve variables xn minus d plus 1 to xn. Some of them. And also the other ones. I mean, there would be mixed. In fact, there's we can check that the ideal is Cohen-Macaulay if and only if this does not occur. If and only if all the variables that occur in my initial ideal are those ones, here and here, okay? So, if R over I is not Cohen-Macaulay, consider this morphism that is going to send the last variables to 1. The xi are unchanged for all I from 1 to n minus d, and the other ones, I'm going to send them to 1. Okay. And let J be the image of my initial ideal. Okay, I'm kind of dishomogenizing. I'm making my variables equal to 1. So the monomials that do not involve those variables are unchanged, and the other ones are going to provide elements when I make the last variables equal to 1 that are not in my ideal. So I'm getting elements in my B0. Okay, so yeah.
For the take the image of the initial ideal, I think do this just on the minimum journey.
I just mean I take my initial ideal and I set it there. That's the extension of my initial ideal. So I can take the minimal generators, make those variables equal to 1, and then I consider the ideal here in R generated by everybody. Yeah, that's it. So you can use the minimal generators to describe your idea. Okay. Okay, so those generators monomials in the initial ideal that involve the last variables will give elements in B0. Okay, so, and the other ones will not. And let's say that for all those elements, so for such a monomial, so what I mean is a minimal generator in the initial ideal that involves also the last variables. So for such a monomial, which I could say, I would denote it that way, it has a part in B0 and a part in A. bring in the last variables. Okay. So for each of those monomials, what I can do, we can consider, let's divide this monomial by my Grosvenor basis, the reduced Grosvenor basis of I with respect to the same order as in the beginning, as at the beginning. The reverse lexicographic order with respect to my omega grading. So, and denote by, say, R alpha, the remainder in this division. So you have a monomial which is not in your monomial in your initial idea. You divide it by your Grosvenor basis, so you express it as a combination of the generators of I, and you get a remainder. The remainder is a combination of monomials that are not in your initial idea. So all of those monomials that are here, this will be a sum of monomials. All of those monomials are not in your initial idea, so they can be written, each of them, as the product of an element with, I separate the variables, I look at the first variable. The first variable would be in B0. It will be under my staircase because my monomial is not in my initial idea. And another monomial which will be in A. So in fact, this allows me to write my remainder in a new unique way as the sum of some polynomial that will depend on alpha and of V of elements in my B0. Okay, the remainder of my division will be a combination of monomial, and this is in A, in the last variables, and this is in B0. Okay, maybe I have several monomials involving the same element in B0, but this will form here a polynomial in A, here my monomial in B0, and my remainder can be written this way. Look what happens. This element is in I, because this is the remainder of the division of this monomial by my Grosvenor basis of I. So this element is in I, and if to each of these elements, I can reassociate. I'm running out of time, I'm afraid. So let me conclude. To each monomial X alpha, there, an element in my free module that was this way, which is simply substitute each of the elements in B0 that appear here by the corresponding element in my canonical basis here. I mean, this is very useful. What we usually do when we construct the usual the usual R resolution. We use the reduction of our Grosvenor basis to build the CDGs, that's exactly doing this. Okay, so this element H alpha is that I would write M times epsilon U minus is the sum of the F alpha V epsilon V for V in B0. So to this element in I associate this element in my pre-module. And since this difference is in I, the image by my size 0 that which is still written here will be 0. So this is a synergy. Each of those elements that we build here is inside the kernel of my size 0, which is here. And the theorem is that those generate the whole CZG module. That's a system of generators of the CZG module, which is unfortunately not minimal. Okay, but fortunately, it's going to be a Grosvenor basis for an ordering that I do not have time to define now, but on the next, on this free module, we can define an ordering in such a way that the way this construction provides a Grosvenor basis of the kernel of this map. And hence we can build the Schreier resolution from now on. We have a Grosvenor basis. It's of the first CZG module, and this provides a resolution of the ring algebra as a module. So we have a Schreier resolution of this A module, which is in general not minimal, but is quite close to the minimal one. And the last result that I do not have to explain, for example, in this example, but I didn't have time before starting the talk to write down what was the result. But applying this method, we get the minimal one. But what we did in this paper after doing this construction is that for any simplicial toric ideal in dimension 1, we detected what makes it non-minimal and just removed this and made it minimal. And we could build the minimal graded free resolution as a module for all those toric simplicial in dimension 3. And I guess I have to stop. I'm sorry.
Okay, maybe in the interest of time, let's first, if anyone on Zoom has a question, now is a great time to ask it before the meeting gets turned off.
My co-author Mario is there. So yeah, I hope he has no question.
Okay, great. Are there any questions in the room?
So it's obviously like a lot easier to compute. So were there examples that we couldn't do beforehand that your new method allowed us to compute the regularity or the number series a lot easier?
Mario should answer this because I didn't mention that he has implemented all this in Sage. Okay, so we have I guess that, but in the very difficult example, both are complicated. But it's supposed to, it runs faster. It's faster to compute. That's because I mean this B0, these people that are under the staircase, this is the usual K basis. The basis has a K vector space of the initial plus those variables that you remove. So this is a command which is very fast. That looks what's under your staircase, and this is just a division with a Grosvenor basis that you have already computed. Okay, so.
But I mean, of course, I mean, the K basis can have much larger cardinality than your original set of generators.
Sure, sure.
So that could be a little bit of a trade-off in complexity.
Sure, but it cannot have. Here you see these are 11. So you mean this can be bigger, of course,
Yeah,
but the degrees cannot be. Since the regularity is under control, the degrees cannot be very high. But it's true that this number does not have to be smaller than this one.
Okay, cool. So maybe let's do other questions offline. And let's think.
Okay, thank you.